Well, a very good afternoon to everybody and a very warm welcome to the Royal Academy of Engineering. This is the fifth in a series of Innovation in lectures, which we started some 18 months ago. The first one was in construction, the second one in business systems, the third one in the auto industry, and then medical engineering. And today's a very important event on materials, innovation in materials. And I'd very much like to thank the Institute of Materials, Minerals and Mining and the Materials Knowledge Transfer Network for co-hosting the event with us today. Now, we've got a strong record of engineering innovation in this country. As the National Academy for Engineering, much of our work is focused on supporting and promoting innovation. And we're currently running a campaign entitled Engineering for Growth, alongside partners from industry, the universities and government departments. And together we're working to highlight the contribution of engineering to the economy, to society, to health and the well-being of our country. And as an academy, we manage programmes of research that are heavily supported by industry at the forefront of innovative engineering. We give prizes and awards for great innovation, and of course the chief one is the Queen Elizabeth Prize in Engineering, £1 million each 2 years. It's our major international award, and of course it sits also alongside the McRobert Prize, which is the UK's top innovation prize in engineering. And one of this year's McRoberts Prize finalists was indeed in the field of materials. A team at Concrete Canvas were commended for the invention of their novel material, a rapid, innovative and adaptable concrete infrastructure that sets rapidly to create a durable concrete surface when sprayed or immersed in water. And in July this year, Professor Mark Miodownik won the Academy's Rook Award for public engagement with engineering. And we're very delighted to have him with us today and are looking forward to hearing his keynote speech. In April, the Academy launched an Enterprise Hub, which is providing a raft of support from 70 of our distinguished Academy Fellows who've had extensive experience in spin-off companies. And the aim is to encourage young entrepreneurs who are in the laboratory to set up their own business and to give them support in all sorts of different ways, including business planning and indeed pointing them towards possible funding for their spin-out operations. We also run an extensive programme of schemes to encourage engineering research and to facilitate closer contacts between the industrial and the academic worlds. And we supported 9 research appointments in the area of new advanced materials, including nanocomposites, metamaterials and advanced metal casting. We do a lot more besides, including our policy studies on specific technologies and their application, and our support for the nation's engineering skill base and our policy advice to government. Today we are launching the reports of 2 such policy studies which relate closely to the themes of today's meeting. The first is a report of a roundtable session on the future of additive manufacturing and its potential impact on UK industry. Seeking to distinguish the hype surrounding 3D printing from the real opportunities and challenges for additive manufacturing techniques, the report identifies the unique potential of additive manufacturing in creating lightweight, customised and bespoke items. And these can have application from aerospace to medicine, and whilst we might not all have a 3D printer at home within the decade, these technologies do offer the promise of transformative methods of manufacturing. And you will be able to find copies of these reports downstairs. The second one, Made for the Future, explores the challenges in creating a sustainable domestic supply chain. It looks at ways of reducing our consumption of resource and energy through new ways of making and using everyday technologies such as mobile phones and washing machines, exploring the potential of custom manufacturing and lower energy, closed-loop recycling, and the report sets out challenges for designers, engineers, and consumers alike. These themes and several more will be picked up in today's talks. We will hear how economic and environmental sustainability are important challenges for advanced materials. Uncertainty in the future availability of energy and raw materials puts at risk the development of high-value products and drives up the cost of materials for a wide range of businesses. And the UK can use its strong R&D base to inspire innovative, sustainable and competitive high-performance materials, products and processes. The introduction of a circular economy can help material resources remain in the value chain for as long as possible. However, this will demand innovation in both material science and business modelling. We need constant innovation to develop novel materials, surfaces and coatings with improved intrinsic properties. These innovations will be used in a wide range of applications across many sectors, including healthcare, the creative industries and aerospace. These are just some of the applications we'll be looking at today. We have a terrific lineup of speakers, and from a range of businesses, organisations, academia, and working across the whole of the material sector. They will share with us pioneering technologies, novel ways of using materials and processes, and how to take new ideas to market. After each presentation, you'll have an opportunity to ask a few questions. It's 15 minutes presentation from each speaker, and I will ensure they don't go over that. And then 5 minutes for Q&A at that stage, and then we'll have a final session of the day in the form of a panel for discussions when you certainly will be able to put many more questions. The event is being filmed for the Academy's website. The refreshment breaks will take place in both rooms next door, and the drinks reception afterwards will take place on the ground floor. I've not been informed of any scheduled fire drills. If the alarm goes, it's for real. So please follow Academy staff who will direct you to the nearest exit. If you wish to use Twitter to report the event live, please use the hashtag shown on the screen. I assume you can read that. It's #RAE capitals NG Innovate. Now, we start with the keynote speech, and I'm very delighted that we have Professor Mark with us this afternoon, Professor Mark Miodownik, the Professor of Materials and Society at the University College London. So it gives me great pleasure to invite Professor Mark to the stage.
Thank you very much for inviting me. It's a great pleasure to talk about this topic. I haven't worked in it as long as quite a few of you in this room, so I feel a bit humbled talking to some people in here, veteran materials experts. Some people even taught me in this room, so I'm very proud to be able to kind of give my take on what I think materials innovation needs to be doing in the 21st century, and also to do it in such a great place as the Royal Academy of Engineering. Okay, so for those of you who are not materials people, I just wanted to kind of point out in a kind of flag-waving way how important materials are. So this is just down the road from here on the Strand, a normal picture. If you start pointing out all the materials on it, it doesn't really take you very long to realise that everything there we created, and they're all made of different materials. And each one of those materials, I haven't even scratched the surface there, I'm pointing them out, each one of those materials was a revolution in its own time. So it's no accident that the ages of civilization itself are named after materials. So the first big step is stones, the Stone Age. If you don't get to the Stone Age, you're an animal. It's official. You get the stones, you get the flint, you work out about toughness and obsidian, you can cut things. But you can't make architecture. You can't cut a tree down. You can't really make a boat. You can't make a car, a vehicle. You can do very little with stone. So you have to make the link to metals, and that was a huge step. And then comes copper, bronze, iron, steel, and they really set the scene for the 20th century, 21st century city and our urban life today. And these materials all came along with them. And I get a little pointer here. Oh yeah, great. You just can't imagine life without them all. Everything is made of something. And each one of these materials changed life. So even something as very mundane, perhaps, as an amalgam, right? Something to put in your tooth when it gets decayed. That changed everything. So that's a fairly recent innovation. Before that, toothache was widespread. If you had bad toothache, you had two options. One, go to the local blacksmith, who was usually the biggest person in the town or village. They would get a pair of pliers, and they would wrench the tooth out of your mouth, and you would be grateful for that. And then you get some metallurgists coming along, and they create a liquid metal that when it goes into the mouth can be poured into a hole, but then it sets and hardens, and it stays put for your whole lifetime if you're lucky. And of course, things have moved on from them, but that's just one example. So if you haven't got toothache now, just spend a few seconds thanking those people who created that stuff. And it's everything, right? So all these materials. So the question is not, is that it? Is that how we done with materials now? Have they all been invented? And I want to just, first of all, then kind of go into the material science of materials, because most of those materials I just pointed to were invented by not scientists or engineers, but just people who had a passion for fiddling with things, understanding how the world worked. And the 20th century real step forward in terms of materials is not so much inventing them themselves, like concrete and steel were all invented centuries, in fact millennia before now. The real innovation of the 20th century was working out why they are so good and how they work. And this all comes down to scale. There's a paradigm in material science called the structure-property relationship. And it's all about these different structures inside materials. And just to kind of make that point, so here we are. Here is, things are big at the top and they're small at the bottom. So trees, whales, mice, fleas, hair, tissues, cells, organelles, DNA. That's the natural material side of the world. And we all know those structures exist. And we all know, really, that they are very important. Each one of those is very important to how we function, how our skin functions, our bone, our hair, all these things. And of course, the 20th century was really working out that the inanimate side of the world, concrete, steel, rubber, amalgam, plastics, all had those scales in them. And that if you could control those scales, you could control the properties. So down here is a sort of crystalline micro scale, and working out how these different crystals in steel or titanium or superalloys, how they all work, how the boundaries fit together, how that influences strength. That has been a huge leap forward. And without that, you don't get turbine engines, you don't get the aircraft industry. And down here, this is a single crystal of silicon, and working out how to make one of those pure enough that it does work every time you switch on your computer was really difficult, but has been achieved. And that's through the sort of amalgam, the theory and the microscopy of it all. So you fit a few billion of those together and you get a computer or a mobile phone. And so this has been our big triumph in the 20th century, is putting together the scales of buildings, robots, phones, tiny microelectronics, little machines, crystals, single crystals. Down here, a big exciting area called nanotechnology, and then of course the atomic scale. Now, so that's the 20th century, and we kind of know all those scales, and everyone's doing work in each one of those scales. You can spend a whole lifetime, people do, in one of these little crystal scales. So, what should you do if you're setting out to do something for the 21st century materials? Well, the first thing I think we've got to admit is that we are all extremely wealthy. I mean, really, relatively. We live like kings. We've gone a long way since the Stone Age. So it isn't really about trying to get perhaps more material wealth that we should be worried about, I think. But actually trying not to trash the planet while maintaining this way of life. And that's going to be two things, energy and environment. And so how do we maintain all of those materials in our and hone them down, make them better, while also keeping an eye on sustainable energy and environment? Those things are not easy, and I'm not going to try and attempt to solve them or really go into them in huge details. So I'm just going to do some little pinpricks into it. And one of them is solar cells, because it's a really big materials innovation that promises to deliver a lot of our electricity in the future. There is more sunlight coming down on the Earth than we could possibly use in terms of energy. I mean, by orders of magnitude. So it's raining down on us, this energy, and all we have to do, it sounds easy, is harness that energy and turn it into electricity or fuel, and we're kind of done on the energy front. We don't have to dig up oil, coal. We don't have to use wind, even if we don't really want to, or water. We don't have to use nuclear. If we could just crack this material science problem. But it hasn't been cracked yet. The efficiency of solar cells is very low. How do you do it? Well, of course, it's all about scale. And down here, at the nanoscale, is where a lot of people are focusing their efforts, trying to change the molecular structure of things that harvest photons and turn them into electric energy. So this is semiconductor research. It's a huge amount of materials modeling that's going on, which is really exciting, which is, in a sense, cuts down the number of experiments you need to do. And this is all very, very mature science now. So using quantum mechanics can really push ahead this kind of technology. And then there's the micro machining and nanofabrication. So these are little hairs that people have been building to harvest light and make the efficiency much higher. So control of microstructure and nanostructure and the understanding of the fundamentals is really coming on apace. And you're kind of waiting for any moment now for someone to make an enormous leap forward in the efficiency of these things. But I don't want to just say that it will be solved down here, because my main message today is that it won't. My main message today is that we live in a very complex world, and each one of these scales is important. So when you think of a solar array in a desert, let's say, or in a farm in Dorset or Cornwall, you have an enormous number of social issues about displacement of farmland, displacement of crops. People ask, why are these things in fields? Why are they not on buildings? Why is the urban environment not full of solar cells? And why are we using farmland for these things? And these are good questions, and questions that material scientists and engineers should not ignore. So solving a problem down here, which then leads to a problem up here, is not a solution. So one of the big challenges we've got is actually linking all these scales together. That finding a solution, maybe for cladding a building, might be a different solution from having a solar cell that powers your calculator. And just sort of saying, well, this solar cell works, so we'll just push that technology forward and cover fields with it, is perhaps not the right direction. So that's one thing I think we've really got to keep an eye on, is linking up these scales and not ignoring the social impact, the cultural impact of the technology. So we need solar cells you can paint. We need solar cells that fit into the built environment. We need roads that harvest energy. I mean, that would be a great way of doing it. So thinking laterally, thinking multi-scale. Batteries is another one where really, with even the best solar cells in the world, we're going to have to store this energy somewhere. It gets dark in the evening and we still want to read and watch telly and generally do other things. So we're going to have to work out how to store the energy. And at the moment, battery technology is sort of stalled. There's good solutions for small things like mobile phones. There's very bad solutions for things like electric cars. And there's terrible solutions for planes, and the Dreamliner episode with the lithium show just how difficult it is to scale up these things. So again, we've got this scale problem where actually we're very, very good at fiddling around down here, looking at quantum mechanics and making little structures and doing lab experiments with graphene and that sort of thing to really push forward battery technology and the electrodes and pushing lithium in and out of places, and also working out why lithium batteries degrade so quickly. This, by the way, is a 3D printed battery, in case you were thinking about that technology, which I'll come to in a minute. But actually, let's think about this. It's got to work up here. It's got to work up here too, otherwise it's not a solution. So should the battery be a discrete component, which is just added on, or could the battery be part of the whole body of the car, or the part of the whole body of the plane? You need a lot of area for batteries. Why not think about a different solution, one that actually recognizes the fact that it's going to be in a plane or a car, rather than just saying we're going to have this battery and we're going to work out the physics down here. So then there's another way of really addressing energy, which is just to use less of it. And this, in terms of transport and airplanes and cars, this is going to almost certainly be a carbon technology. So our civilization is going to have to wean itself off steel, aluminium and titanium onto carbon for most things, I think. And the reason is clear, it's here, is that if you try and get stiffness or strength per weight, which is the specific stiffness and the specific strength, and you look into the corners, what give you the best strength per weight and stiffness per weight? It's the carbon technologies that really win, apart from ceramics, which are very difficult to build stuff out of without it being brittle. So you already see this, of course. So in fierce competition between Airbus and Boeing, it's pushed us in this direction. So by trying to outdo each other, they've actually got to 70-80% by weight carbon composites in the plane, which I think is just absolutely extraordinary achievement. And if you know how hard it is to make a decent carbon composite and how big equipment you need, it's really impressive. But we've got to go further. We've got to not just build planes, but we've got to build cars and probably quite a lot of other things. So I've got a picture here of a violin built out of carbon fiber composite. But this should be, I think, the material of choice when we're fabricating things that need to be held up, where weight's important, like a violin or a musical instrument. At the moment, of course, we use a natural carbon fiber called wood. Now look, it's a multi-scale problem. Here are the fibers. Here is what the kind of layout technology looks like. You've got to put it into an autoclave to get it to set and to be free of defects. And down here is where the problem lies, in some senses, because these fibers don't have optimum strength. They still have quite good strength, but they're mostly amorphous carbon with hexagonal sheets in various different directions. And down here we've got various people doing things on carbon nanotubes, which are essentially probably the strongest, stiffest potential construction material we can ever really hope to have control of. So these carbon nanotubes, if these were this size, if we could get them to that size, all rolled up, and able to build things like this out of them, we could make huge strides in thinness and reduction in weight and therefore reduction in energy. And of course down here the joker in the pack is graphene, which is widely touted and now used as an electronic material, but also has extraordinary mechanical properties. It's kind of the mother material of all of these technologies. And there was a tennis racket in this year's Wimbledon using graphene as a kind of composite material. And this is also potentially really important structurally. But again, I think the big game is going to be mass production of this type of technology into things this big. And if cars are not going to be made from steel anymore, we need to know how to mass produce carbon fiber and nanotubes and graphene into a functional structural material. And if we do that, we can also do things that really avant-garde in prosthetics, because this is where weight, stiffness and strength really matter. We can obviously solve a lot of problems in terms of range of electric cars for a percentage for weight of energy, and I know that a lot of you are going to laugh at this. This is a space elevator sketch, right? So this is how to get into space. You build an elevator 33,000 kilometers long. Sounds mad, and of course it is. But the good thing about this is, one, the only way, I mean, even theoretically, the only way you can make this, the only material that we have ever discovered that can possibly take the stresses per weight that this is going to impose on it is carbon nanotubes. So we know that we have potentially a material that can do it for the first time in history. Two, we are not going to stop wanting to explore the solar system, right? We're not going to stop wanting to get out there. And rockets are really, really wasteful, and they're really not going to probably be environmentally sustainable because of that, in terms of energy density. So we're going to need a way of getting off this planet. Maybe not in 20 years, 30 years' time for this, but this has to come into play at some point in the next 100 years. So why not start building it now? Because we need some big, really outstanding projects to get people excited about it. We need something that's really so ambitious that people can't even believe we're serious. Landing on the moon was one of them. And we need another one. And I think the space elevators are there. Now, we don't have, for all those who are worried about this thing breaking and causing havoc, which is clearly a big worry, we don't have to start on this planet building the first space elevator. We can start on the moon. And the moon's just a bigger problem, right? If we're going to have a moon base, we're going to need a space elevator to get on and off the moon from near moon orbit. So, and of course, if we have some problems in the early days of the moon elevator, it's not going to kill anyone. So, I know it sounds science fiction-y, but we need some big projects, and I'm for this one. Okay. Now, another materials challenge, I think, is not just what we make things out of and how we do it, but it's this. We can't just end up putting most of what we make into holes in the ground. Well, let me qualify that. We can keep doing that. There are plenty of holes in the ground, and probably when the population sort of levels out, we could probably carry on doing that for 100 years without really any problem at all. So we could stop doing that, but we shouldn't. And why shouldn't we? I don't think we're a credible set of people if, as a civilization, we can create all this wonderful stuff, do all this crazy stuff, and then our solution, our sophisticated solution for getting rid of it is putting it in a hole in the ground. To me, that speaks that we can't be bothered. We're not intelligent enough, or we just haven't got enough. We can't put our effort into that. And so I think we're talking to the public directly every time something goes into a waste bin, into landfill. We're saying we haven't worked out how to do a complete life cycle analysis of all the materials we create. We create these amazing materials, but we don't know what to do with them. And the nuclear waste industry is a really bad example of this. So that's what most people are worried about nuclear. And essentially, we need some big examples of complete closed loops of lots of our manufacturing technology and materials. One of them is a possible one, is 3D printing. And I say this, it's not obvious why this should be such a good way of doing it. But creating things that stay around for longer is one really good way of reducing waste. And this is the case now, if your washing machine breaks, and who can really withstand more than 3 days of their washing machine being down, right? The alternative is the ignominious walk to the laundrette, okay, with these enormous piles. And it just doesn't stop, like every day you have to go there. So washing machines, important things. But if they break, it's about 3 things in a washing machine that will break. Otherwise, it would last for about 30 or 40 years. So why not make those 3 things? Why not force manufacturers to make those 3 things out of things that can be replaced easily and be printed? Because then you haven't got this problem of, you've got a 10-year-old washing machine and they don't make the parts anymore. How often have you heard that? They don't make the parts anymore. So you're going to have to scrap it. We're going to have to throw it in the waste, and then we have to buy a new one. So I think one of the big wins for 3D printing is going to be getting rid of this idea that you can never get a spare part for something and building things for the last 50 or 70 years. The other great thing about 3D printing is just the extent in which people, again, can get very excited about engineering and materials. And this dress was made for this woman. It only fits her. And in case you think it seems a very stiff, this is a fully articulated dress. And the idea that you're not going to make things that are just for anyone, that people are going to have their own bespoke things. Well, that's going to perhaps change people's relationship with the objects they buy, make them more personal, make them last longer. And then, of course, you've got the huge potential of the social side of 3D printing, because now, of course, people are starting to share the digital information. So I was talking about the digital information for a spare part. But what if the spare part is a piece of your body? What if you have lost a hand, an arm, a leg? Right? This could be as a result of an accident. It can be a result of being in a war zone. It can be a result of many, many things. There are millions of people worldwide who cannot afford a top-of-the-range prosthetic, which is going to set you back about £20,000. And even then, it has a lifetime that's not that great. So why wouldn't you print out an artificial hand? And that's exactly what people are doing. They're sharing information, printing them out. And this is the hand of a child whose parent bought a 3D printer, so that as they grow up, he can keep printing out different hands, and the child can get involved in designing their own prosthetic hand. It's all built and printed by themselves. And there's something really liberating about that. And again, changing your attitude towards what is engineering, what is materials technology. And of course, it's not just plastics and things like that. Metals are going to be a huge part of all this, and this is, Airbus and lots of other big companies are honing their every single ounce of weight off their airplanes using 3D printing by making things that you wouldn't be able to actually afford to make, small parts with tiny holes in them everywhere to reduce the weight, but still have the same strength and stiffness. Am I running out? No, I'm not.
Admiring the way you're taking weight out.
Oh yeah, taking the weight out, yeah. And so little by little, 3D printing actually, this saves a huge amount of money and a huge amount of energy over the lifetime of the aircraft. And this is happening in all transport areas. So although, in the mass production area may not replace things. In the bespoke part area, it's going to be very, very important. And this, of course, I can't resist, is kind of do a sort of scale map of this. So clearly you can make robots that build buildings. People have already done it. You can build bespoke dresses, shoes, there's one downstairs. You can do metals. I told you before you can 3D print solar cells and you can 3D print batteries. So this means you could encase your whole object in a battery, or it could be part of the whole object in the same way as humans, we have energy generation distributed throughout us. And of course, there's massive opportunities because down here, the design of alloys and materials for printing is probably the biggest opportunity in material science there is. And UK is very well positioned to do this. And we can't print at the nanoscale down here. This is probably 100 nanometers is probably the largest feature size so far, but people are working in that direction. And so there's a huge opportunity here, and it's a very exciting field. And then, I should read 3, sorry, in case you're panicking. The other thing I think is a really big opportunity for materials is the biological interface. Not least because all of us, even if we don't want to live forever, we don't want to die in agony. We don't want to have a peak of mobility and then spend the last 30 years of our life essentially either wheelchair bound or in great pain or having to go to dialysis once a day at the hospital. So there's an enormous market for people who want a fully functional old life, and this is going to be the way to do it, is create materials that can be implanted into the body and can replace body parts. And it's happening. This is perhaps the most impressive example recently that I've come across, which is this is a professor at UCL who's created a windpipe in exactly the right shape for the patient. They had cancer of the throat. The only solution is to cut it out and to talk and breathe through a hole in your throat for the rest of your life, unless you can have a material that will replace it. And there is no such material except for now. And this is a scaffold material. So you create a scaffold where cells like to be. And they like it so much that they basically eat the scaffold up and replace it with living tissue. And of course, this is 3D printed to the exact shape of the windpipe of the patient, taken from the MRI scan. So you take the digital image, you create a physical prototype, you put the stem cells in, you put it in a bioreactor for a few weeks, and then you implant it into the body, and this patient is still alive today. And that's really impressive. And of course, people are fast forwarding to other solutions. So this is a 3D printed jaw, titanium jaw put into a patient in Belgium, again last year. And this is really going to start happening more and more. And of course, people want to get to the point where they have livers and kidneys, because not least because there's a huge shortfall in terms of donors, but also people in the third world are having to sell their livers and kidneys, or they feel they're having to sell them, to people in the first world, because they're worth so much money. And so by cracking this, we can really change quite a lot of people's lives and stop other people having to sell their organs in order to stay alive or to feed their families. And it isn't just, the biological interface isn't just in the body. So this is a picture of some self-healing concrete where the biological interface is in the built environment. So inside here is bacteria, which repairs the structure once it gets cracked. And it's a particular bacteria that likes to eat starch, which is embedded in this concrete, and it excretes calcite. And so this covers 90% of the strength of the concrete if it's cracked. So I think what's going to happen is that we're going to understand more about the body and putting materials into the body and replacing body parts, but we're also going to make the built environment more self-healing, self-monitoring, and become more biologically kind of alive, if you like. And self-healing materials they seem like science fiction, but they're coming. There's self-healing plastics, self-healing composites, self-healing concrete. And I guess just the last thing I want to say really is that, I think the big challenge is to solve all these problems, is this linking up of the different scales. And biology's done it. Biology does it so brilliantly. When you change a gene down here, you don't magically change the colour of the leaves or the eye colour of the mouse. It changes every scale along the way. And we've got to learn to do that in the built environment and in all materials. And if you look at these different scales, you realise that we have different specialties, which we have to have. It's really important. So we have architects and engineers, civil engineers up here. We have mechanical engineers and roboticists, and we have designers. We have jewelers. We have mobile phone makers, we have artists, we have different people who are different experts at different scales. And down here we have chemists and physicists and material scientists. And getting them all to talk to each other, to create solutions that really make sense over multi-scale is hard. And I think that is our big challenge, is that materials, I don't know how many chefs, biologists, designers, architects we've got in the audience, jewelers, but all of these people, in my view, need to be part of this project. And if we don't have them in there, we aren't going to produce solutions that people are going to want to use and accept. So we've got the social and cultural side of it, and engineers and material scientists are not expert at that. They need to get experts in, and these are the people who are called architects. They're called designers. They exist. They're brilliant at their jobs. So we need to start working with them. But we need to start working with them right from the beginning in a project. And this is what we're doing. I just want to show you one of our projects, just so that I'm speaking the same thing as I'm saying. We're trying to make a wearable exoskeleton in one of our projects, and we've got the surgeons and psychologists involved right from the beginning. We've got civil engineers right involved, mechanical, biomedical, chemists, all working as a team, all trying to solve their individual scale problem, printing electronics, printing the mechanics of a bodysuit that can articulate but also actuate, working out how to do the chemistry and physics of that, but also the psychology and what the patients will actually want to wear. So talking to patients. And this is kind of our method for doing it. Created a place called the Institute of Making, and it's basically a place in the university which isn't owned by any one department. Is a sort of cross-faculty place where when you want to start up one of these projects where you're trying to solve lots of different scales at the same time, you don't do it in isolation. You create a whole space where all those people can work together. They can go back to their individual departments to do the individual bits of work, to look down the microscope or do the bit of chemistry or do the bit of electrochemistry, but they come together to build the whole prototype in one place. We call it the Institute of Making, and we also kind of nurture a multidisciplinary working environment there. And I think this is one of the things we need to do, is cross those boundaries more and more. So yes, I'd just like to finish there and say thank you to, don't do the stuff I do on my own, and I'm part of a big community, and have PhDs and RAs and inspirational people, Anthony Finkelstein at UCL, who really I think has got the message and is pushing ahead. He's the Dean of Engineering. But the funders, of course, are also just very, very important to us. Without them, we couldn't do any of this stuff. I'll end there and thank you very much.